Hello all, welcome to another episode of Data Science Foundations. Last time we learned probably one of the most important theorems. It depends, it's kind of a little almost too obvious in all of statistics, called the plug-in principle. We learned that the best way to figure out some function or summary statistic, as we were talking about before, of a population. And summary statistics are useful, again, because they answer real-world questions. So the best way to answer a real-world question about a population you don't have answered or have access to is to ask that real-world question of the sample. Okay, so we learned something really useful, but we also mentioned some trade-offs and some catches. Do we remember what they were? So first, the trade-off is that the more data you have in your sample, the better the plug-in principle will be. And we sort of prove this sort of de facto in the fact that as the sample approaches the size of the population, it's just going to be the population, and so obviously the plug-in principle will work. This isn't like a formal proof, I didn't show that it sort of monotonically gets better and stuff like that, but hey, we're trying to be a little bit practical here. And then the second thing that we learned was the catch. This is sort of the big thing for the plug-in principle. The catch in this case is that the plug-in principle might be the best estimate that we have. Okay, so it's a consistent estimate. However, it might not be a good estimate. Okay, so even though we can say it is the best one we've got, maybe it's just not good at all. And so we shouldn't be estimating this statistic from the population. Okay, so today we learn how to sort of solve this problem. So we're going to learn how to make a confidence interval, and the confidence interval is sort of our solution for this. We learn how to apply Bootstrap to get that confidence interval, and then we learn what happens to the confidence interval as the sample sizes change. That's the learning objectives today. I'm hoping that we're definitely going to get through them. Okay, so I want to start off with sort of an interesting phrase. Something's not normal here. And for any of those, I've heard this a lot. So for any of you that are familiar with a classic statistics course and even classic machine learning courses, and I honestly believe that more are going to be shifting more towards my style, is that normally you teach the central limit theorem, which you guys may have heard of, and I'll include a link to in this video, and you teach the normal distribution, and that's how you generally get confidence intervals. Okay, but there's two problems with this. Okay, problem number one, this requires a lot of statistics. Okay. To really sort of understand the central limit theorem and not just sort of like hand-wavily do it, you need to know a lot more about random variables than we already do. It's a sufficiently long proof. I mean, this is somewhere around 2/3, 3/4 of the way through your intro to statistics class. So generally, it's a full class value of stuff that you need to learn. And then the second thing, the normal confidence interval isn't even valid for some types of functions, which is not true for the plug-in principle. So, for example, the normal confidence interval it doesn't work necessarily well for things like the median, or if you wanted to do something even more arcane than that. So, for example, doing confidence intervals, and so I'm doing something called I've done causal inference before. I'll include a link for this, but if you wanted to do some types of arcane confidence intervals with causal inference, so for example, you're using the parametric G formula, you want to do a confidence interval for that, it just won't work, right? You really need to rederive it, and the rederivations are incredibly complex. So I'm teaching you what I think is an easier to learn, as well as a more powerful technique to do confidence intervals. Why we're still teaching the normal stuff is somewhat beyond me at this point, but hey, so something's not normal. There are reasons, so I don't want to sort of offend people here. But this is sort of the way that we've chosen to go about it, because I think it's a little bit of an easier path, as well as a little bit more of an expressive path. Okay, so that's why we're not doing sort of the normal way. Back to the assumptions. Remember, we couldn't use the plug-in principle without the assumptions that we have. The assumptions that we have are simple. First, we have the data, right? So we've got the data. If we don't have any data, we can't make any inference. Second, it comes from a random variable x, okay? And we get IID samples from that random variable x. And so this is kind of like just the initial thing that we had learned. If you've got a random variable and you're able to take samples from it, and you want to learn summary statistics about that random variable, then what do? You simply take infinite samples. And if you can't get infinite samples, well, then 10,000 is probably good enough. This plug-in principle is kind of like a restating of this original idea that to figure out the mean of a random variable x, you take samples and then you take the mean of those samples. It's very simple or similar for a plug-in principle because we assumed that our population is a random variable. Okay, so that's enough recap. Let's get into the real stuff. Okay, so the real stuff, I'm going to start off by asking a question, and this question will sort of lead us to a really interesting result that will allow us to make some pretty cool claims. Okay, so the question I want to ask is, let's say we had a population, so something like this down below, and this can be, the, number of really happy events in someone's life or something like that. It doesn't matter, just trying to stay positive. Okay, and let's say you were taking samples from this population 10 at a time and finding their mean. Okay, so what would you expect the mean of the samples to be? It's pretty simple. To be exact, I'm kind of looking for a range of possible means. So let's say if we had this population, we took samples of 10. What would you expect the sample mean to be? So I'm gonna go ahead and I'm gonna take lots and lots of samples, and then I'm gonna show you their sample means down below. So I've gone ahead right here. I've taken lots of samples from our distribution up here, our population distribution. You can see this right here. So I take a random choice from our population distribution. So I take 10 of them. So I've taken 10,000 samples of, I guess, 999,000, whatever. So I've taken 9,999 samples of 10. So in total, so let's assume that this is just 10,000. I've taken 100,000 individuals from our population, and I've questioned them. Okay, and I go ahead and I plot this distribution down below. It's called a sampling distribution. It's something that's pretty important. So I plot this distribution down below. It looks something like this. And then I go and I ask you, hey, let's say I'm going to take a new sample from this sampling distribution, right? And I'm going to calculate its mean. Okay, well, where's the mean likely to be? Is it likely that I'll have a mean of 30? Yeah, seems pretty reasonable. Is it likely that I'd have a mean of 40? And sort of here, intuitively, you could look at this sampling distribution, you could be like, well, it seems incredibly unlikely. I mean, yeah, I guess it's maybe possible. No, so we took 10,000 samples. None of them had a mean of above 36. So it's probably really unlikely. What if I said, is it likely that they have a mean of 34? And you could sort of look at this and you'd be like, well, it's possible. Some of our samples had a mean of 34. Some even had greater than 34. So it's possible. So you've got this sort of intuitive view of how likely it is that we get means of a certain extremeness. So I want to formalize this. So the real question that I'm asking is, I'm asking a question of what is a range of possible means that I could get from my sample that I should expect 99% of the time. Okay, and then things outside of that mean, they might happen 1% of the time, but they're very unlikely. So let's figure this out. So one way that you can phrase the question that I like is, how far from the actual mean do you expect your sample to be? Okay, how far from the actual mean do you expect your sample to be? And we can calculate this. So, for example, let's say we were looking at, so in this case I'm looking at 5, so I squared everything. So I'm looking at, hey, what percent of the samples that I took up above, okay, were more than 5 distance from the actual mean of the population? I calculated that, and it turned out to be 0.3%. Okay, 0.3%, that's pretty good. So you can probably go back to your boss and say, hey, based on the data that I've collected, simulations that I've run, it looks like, and so I've kind of made like a new random variable here. So it looks like I expect that the sample mean, in this case, there's going to be a less than 1% chance that any of our sample means are going to be more than 5 away from the true mean, right? You go back to your boss, you say that. That's kind of what we've calculated here. That's kind of cool. So what did we say? I just want to recap what we said, because you can sort of go through this little exercise and kind of figure out like, oh, what's a range of possible sample means that I'd expect from our true distribution. And I went ahead and I phrased it in this specific way. And yeah, well, let's recap what we just sort of proved, what we just sort of figured out. Okay, there's less than a 1% chance that a sample mean is more than 5 away from a real population mean. That's what we said. Let's go ahead and rearrange the order of this. So and this doesn't matter. All I said is one was within some distance of another. Let's rearrange the order. There's a less than 1% chance that the real mean is more than 5 away from the sample population mean, or from the sample mean of the population. That's really cool. So if we knew this information, right? If we knew that, hey, if we took a sample, right, from our population, and its mean was very likely to be within 5 of the true population mean, then we know that, hey, even though the plug-in principle might be a bad estimate, it's at least within 5 units, whatever this may be. It's 5 inches, 5 years, whatever, of the true population mean. This is really cool. In a way, we've just sort of specified a range of values that we can truly expect the population mean to be in. So we might not exactly know what the real mean height of people are in the United States, but we can get a really good estimate of it using the plug-in principle. And then we can use the plug-in principle in another way, which I'll sort of show you right here very formally, in order to get a little interval, a range, where we can say, hey, we're actually sure that it's going to be within 1%, or it's going to be 99% of the time inside this range. This is a much more powerful thing than just saying our best guess is here. Because not only do you say it's your best guess, but you give your confidence at how good that guess is. And it's a range, so that kind of sucks a little bit, right? So you don't exactly know where it is in the range, but at least you know how confident you are in it. So this is kind of the new power that we get with a confidence interval. Okay, so how do we get there? Let's go back. Let's review how we sort of got there. So how do we get there? We've got 2 steps that we used in order to calculate the above. So 1, we sampled from the distribution a lot of times. Okay, and then after we sampled from the distribution a lot of times, the true population distribution a lot of times, we applied the function that we were interested in this case, the mean, to get the sampling distribution. Okay, and then 2, we found the distance from the true mean of the population such that the sample means would have a less than X% chance of being further. So that's kind of how we calculated our confidence interval. Now here's a problem. The problem required that we had the true population distribution, right? The true population distribution. So we're stuck. We don't have the true population distribution. In fact, we only have the sample. So what do? We're trying to compute a function on the true population, and we only have the sample. So what do? Oh, this is what I love. So you of course use the plug-in principle. Right, like this is just magical. The great part about the plug-in principle is it not only gives you the estimate, the plug-in principle is used to estimate how good the plug-in principle is. I mean, that's a nifty tool. Okay, so you guessed it. We use the plug-in principle. We have a function. The function is simple. We sample from the distribution, aka the sample, lots of times to make a sampling distribution. We then find the distance from the true mean, aka the sample mean, such that a sample, so a bootstrap sample, a sample from the sample, would have a less than X% chance of being further. Let me show you the code for this. So it's pretty simple. Excuse me. Okay, so we go ahead, we sample a sample. So this is, in real life, this is exactly what we would have access to. This sample right here. So this is in real life what we'd have access to. Okay, just like we did before, we go ahead and we sample from the sample. So this is a sample. We sample from the sample. We sample, in this case, 10 from the sample, because this is what we would have done in the population distribution to figure this out. The only difference is we sample with replacement. Okay, and we talked about why we needed to sample with replacement before. We then take the function that we are interested in this case the mean, for each of these samples. Okay, and we do this 10,000 times. Doesn't really matter. And so now we get what I call the bootstrap distribution. It actually looks surprisingly similar to our real distribution. The one thing that you might notice is it's a little bit shifted. We got a kind of a wanky like sample here. So anyways, we go back here. So the second step. So that was the first step. The second step is that we take our bootstrap distribution, we subtract the true mean from it, in this case, and we find the percentage of times that the samples would be more than, in this case, 5 away from the true mean. And these are samples from the sample would be more than 5 away, and this is something we choose, than the sample mean. So the samples from the sample mean would be more than 5 distance away from the sample mean. And we go ahead and we find the number of times that happens. In this case, it looks like it's 1% of the time. So our plugin principle would say, hey, if we took a sample from our population distribution and we looked at that sample mean, the true mean of that population distribution would be within 5 distance of it 99% of the time. Cool. One quick question that people often have that I think is relevant here is how do we find out which 5 distance we should use? Well, so in this formulation, you have to just try lots of distances. And so you can just iteratively try distances until you find something that's close enough to the percentages that you want. Okay, cool. Now that you've learned how to sort of make this confidence interval by hand, I'm going to show you one trick to make it a little bit faster. Then I'm going to give you some caveats. So the trick to make it, so yeah, I literally write this down. So I hope you're smiling now because this is just awesome, right? I mean, how often is it that you have a tool that you learn has a weakness, but you learn that the tool is the solution for the tool's weakness? And it's very rare that you see that. So it's like I don't really even, it's like Superman's whose weakness is kryptonite, but he can use kryptonite to fight off the kryptonite. It would just kind of be like it's very meta. So anyways, so I hope you're smiling now. The first time I saw this was like magic to me. I told you I read this initial book, so where I kind of first learned about this, I think like 3 times. I keep it on my bedside table. It means that much to me. What we can go ahead and we can do at this point is I can sort of show you a nifty trick. So there's one shortcut that I'm going to use throughout the class, and this is called the percentile confidence interval. It's a pretty simple change. It makes one more assumption, which I'm not going to tell you how we get this assumption, but I will tell you how, but I'm not going to prove it to you. It's that the bootstrap distribution is symmetric. So as long as the bootstrap distribution is symmetric, then we can go ahead and we can use this percentile confidence interval, and this is fine. The reason why it's fine is we have something called the Bootstrap central limit theorem, which allows us to make this claim. This is sort of the normal basic bootstrap confidence interval that's taught. In this case, instead of kind of finding the true mean and then looking on some distance on either side, we assume that the random events, the extreme events, are sort of symmetrically distributed. And what we do is we trim off so in this case, you take the bootstrap distribution, you trim off the 2.5% of the extreme events on the right, and we trim off 2.5% of the extreme events on the left, and lo and behold, you are left with a 100 minus 2.5 minus 2.5% confidence interval, aka a 95% confidence interval. So that's kind of cool. And this will kind of automatically do the confidence interval for you. So in this case, we get, our confidence interval in this case is a 30.3 and a 38.5. So pretty cool. I'll show you 2 more tricks that can kind of save you a lot of time when doing this a little bit later on. So this is the SNS. So Seaborn has a go ahead. They've got a pretty good way to visualize confidence intervals. So just do a point plot on your sample with a confidence interval of 95. And so in this case, it will sort of visualize the confidence interval that you want. And of course, you can go ahead and you can use the sns.algorithms.bootstrap in order to go ahead and bootstrap for you. And then you can figure out the percentile confidence intervals afterwards. Okay, so there's a lot of caveats here. So Let me first just go ahead and talk about the true caveat. And I asked it as a question. Wow, this is a long video. I hope you guys are really interested in confidence intervals. So where does the randomness come from? Okay, it's a 90% confidence interval. That means that we say 90% of the time, the true population mean is within this range. Okay, where does the randomness come from? Some people suggest that the randomness comes from the true population mean kind of shifting around. So sometimes the true population mean will sort of be randomly put in the middle of your confidence interval. Sometimes it will be put on the edge. Sometimes it will be put outside of the confidence interval. Is that right? I don't think so. The true population mean is fixed. It's out there. It exists. If we could measure it, it would just be a single number. Where does the randomness come from? In this case, I think there's only really one place where the randomness comes from. It's getting that sample initially. Okay? The randomness comes initially from grabbing that sample. And this is something that we will explore later on, because later on we'll talk about machine learning and we'll talk about the bias variance trade-off. And one of the questions is, where does the variance come from? So it's the same thing. The randomness comes from you randomly taking that sample. That's where the randomness comes from. So it's by taking the random samples, we get random estimates of the population statistic. So looks like I'm phasing out a little bit. It's okay. We can go without me. So that's what when we say we're 95% confident, what we mean to say is that if we take our confidence interval and we repeat this 95 times, or I guess 100 times, then 95% of those confidence intervals that we would make would contain the true population mean, and then 5% of them would not contain it. But we generally don't do this in practice because we don't have access to the population distribution. So, okay, second caveat. We should definitely, I guess this is more of a trade-off. I've got to mention this trade-off so that you don't sort of get angry at me later on that I didn't mention it. And this is something that you'll see as well. So as we get bigger samples, we get better estimates. So we can see this really visually here. The more samples we get, the confidence interval will decrease because we are more confident in what the true population parameter will be. So in this case, as we get more samples, the confidence interval will get bigger or smaller. It will get smaller. This is, again, one of these trick questions you'll get in data science intervals. In this case, so you can see this right here. If the sample size is 5, we get a very big confidence interval. In this case, almost 10 is sort of the full width of it. But if the confidence interval, or if the sample size is 50, so 10 times that, our confidence interval becomes much smaller. It becomes like 2 or something like that. Okay, so again, as you get more samples, the confidence interval gets tighter. We get more confident. Remember, the confidence interval was derived from the plug-in principle. And what do we know about the plug-in principle? We know the fundamental trade-off is the more samples, the better the plug-in principle works. Okay. So I want to mention one final thing. There are different confidence intervals. The confidence interval that I taught here is kind of like, it's a pretty widely known one. It's fairly used. If you're doing some sort of super big data type stuff, this is something that you could use. It would be totally fine too. However, if you're working with smaller data, you probably want to use a more accurate confidence interval. Probably the bias corrected accelerated confidence intervals is the one that you want. I'll go ahead and I'll put a link down below to where you can sort of find implementations of this. Okay. So why this matters? Well, this is pretty obvious as to why it matters. The reason why this matters is because if you are interested in learning anything about the population, right? The best way to do it is by making a confidence interval around whatever you're interested in the population. Giving just the plain estimate leaves out a lot of valuable information, which is how confident you are in that estimate being correct. So remember, all these techniques rely on our assumptions. We've totally aced the learning objectives here. I've gone ahead and I've included some comprehension questions as well. So if you want to go ahead and pause the video and answer these, please do. As always, when you answer these questions, you can go ahead and you can put comments down below with your answers. I'll go ahead and respond to what I think the maybe correct answer might be. If you see an answer that's pretty similar to the answers that you've done before, just go ahead and give them a thumbs up. No need to sort of repeat this lots of times, even though more comments is better, I guess. As always, if you don't feel like leaving a comment down below with these, you can always like this video or subscribe. Okay, thanks so much, and I hope you guys learned how to make a bootstrap confidence interval.